All right, so some types of, or some examples of elastic collisions include billiard balls being approximately elastic. Really, any large object, there will be some conversion of kinetic energy into other forms such as heat, but billiard balls are very well approximated by elastic collisions. Interactions of atomic and subatomic particles many times are elastic. It kind of depends. There's different situations. If you have, an electron getting captured by a proton or something, then they stick together afterwards, and that would actually be an inelastic collision because you've converted kinetic energy into binding energy of that system. But if you just have like two electrons and they bounce off of each other and they they don't create any other particles in the interaction, then that would be a good example of an elastic collision. What we'll be using is the carts on the tracks that we've been using. They have magnets on the end, and we'll be using them such that they repel each other, and that approximates an elastic collision fairly well. What's happening there is as the carts get close together, the energy will actually be converted from kinetic into potential energy that's stored in the magnetic field. But then when the magnets repel each other and the carts separate again, almost all of the energy will be converted back into kinetic energy. So overall, it works well as an elastic collision. So what we're going to do now is look at solving this problem. So what we have here is if we use conservation of momentum, we have m1v1 equals m1v1, and I'll do primes, I guess, instead of initial and final. Prime will just mean after the collision, and no prime will mean before the collision. Plus m2v2 prime. And we're using that the momentum of the second object is 0 at first because it's at rest. So we can also write this as just p1 equals p1 prime plus p2 prime. Now, since we're looking at an elastic collision in this case, we can also use that the initial and final kinetic energies are equal, and we'll use that with p squared over 2m for the kinetic energy. So we have p1 squared over 2m1 equals p1 prime squared over 2m1 plus p2 prime squared over 2m2. Now, what we can do is use this to rearrange and say that p2 prime is p1 minus p1 prime. Plug that in here, and also we want to move this p1 prime term to the other side. So, and we'll get rid of all the 2's as well. We don't need, there's a 2 in all of the terms. So we don't need that. And what we'll have is rearranging the mass term as well. We'll have m2 times p1 squared minus p1 prime squared is equal to m1 times p1 minus p1 prime squared. Let me rewrite that 2 there. Now that we can use that the difference of squares is equal to p1 plus p1 prime times p1 minus p1 prime. So here we get P1 plus P1 prime times P1 minus P1 prime. Now we have this term here and this squared, so we'll cancel those. Here, well, 1. And then we can rearrange this, grouping the terms with P1 and P1 prime. And what we get is P1 prime times M1 plus M2 equals P1. And we're moving the P1 prime terms over to that side, so we want M1 minus M2. Or P1 prime is equal to M1 minus M2 over M1 plus M2 P1. And we can just plug back into this to get P2 prime. It's pretty simple algebra. And I'll just write the result, which is that it's 2M2 over M1 plus M2 times P1. So that is how we solve for what happens in a one-dimensional collision, elastic collision, where the second object is at rest. And really the nice thing here is that actually, if you think about things in terms of reference frames, you can always change the reference frame so that one of the objects is at rest initially. So you can use this to figure out the more general case where they're both moving in the default reference frame. But I'm not sure how much you guys have gone over reference frames so much, or yet. Anyway, I'll also go over the case of the perfectly inelastic collision where the objects stick together in a second, but that will be a different video.